This is a way of saying, if I have a composite airplane that's 30 years old, how do I analyze that without absolutely destroying it? So that's just a big area of growth. And there's a lot of cool equipment, cool technology. If people are wanting to get engaged into robotics, that's a good avenue to get into, that you really do need to understand materials to have the background and know why you're doing what you're doing and why it's important.
Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out. And before we get started, just wanted to mention that we have released material science merchandise for those of you who want to support us or just express your passion for MSE. You can check out more of the designs at itsmaterialworldpodcast.com/shop or by clicking the link in the description. All right, let's get right into it.
Today's sponsor is MatMatch. With MatMatch, you can find materials for your projects in their free database of thousands of metals, polymers, composites, and ceramics. For example, you could search based on a given mechanical property, such as hardness or tensile strength, or simply search by name to find more information about a specific material. You could also find and contact suppliers if you have questions about a certain material, and join more than 2 million engineers and designers who use MatMatch every year. To join, simply go to matmatch.com and start searching for free today. All right. Hi, everyone. We are very excited to introduce today's guest, Nina Gerber, a materials and process engineer turned manager at Boeing. Her undergraduate research at the University of Washington focused on plasma treatment for composite bonding surfaces, which has translated well for her internship and ultimately full-time experiences at Boeing Composite Fabrication Shop in South Carolina. We're looking forward to discussing the role of materials in aircraft assembly processes. So thank you so much for joining us today, Nina.
Thank you for having me. I'm really excited to be here and excited to speak with you guys and get more people engaged in MSE.
Yeah, exactly. We're excited to have you. And so we wanted to start with the composites world. So your role focuses on composite fabrication for the last two sections of the fuselage where passengers sit. And so I read online that the Boeing 787 fuselages are made out of a carbon epoxy composite. So I was just curious as to what properties make this composite suitable for aircraft applications.
Yeah, so first I'll just explain what the carbon fiber epoxy, what Absolutely. It is, right? So first and foremost, a composite is going to be a material made of multiple materials. That's a really simple explanation of what it is. Mm-hmm. But when we talk about carbon fiber and epoxy, or some people are going to call it CFRP, so carbon fiber reinforced plastic, you're imagining actual fibers of carbon, which some people might see it's black fiber, and it is surrounded by an epoxy matrix. And what's important about that is when this material, it cures and it forms specific crosslinks between that resin that gives it an improved strength, durability, and it has great resistance to temperature and corrosive materials. So that's really the basis for why it is a great material structurally. But the other important aspect of using composites in aerospace is that you get those structural properties while reducing your weight. So that's huge. If you read on Google or anywhere about why the 787 is so successful, it's because it's a more efficient airplane. We have reduced weight. That's what makes it more efficient, right? And then also we're able to pressurize the airplane differently to make it a better flying experience for folks in the airplane. So that's pretty huge. I think that's the biggest thing, that when people get excited to fly on an 87, they think, oh, like this is the first structural composite airplane, and I'm going to feel better when I get off this. I'm not going to feel as achy or dehydrated. So that's some of the bigger benefits of having a composite airplane. But I also want to reiterate that that's not the only composite that's on the airplane or other airplanes out there, right? So there's plenty of other materials like fiberglass composites, Kevlar, and thermoplastic materials that are used throughout aerospace that have different properties that make them useful.
Interesting. So has it always been, a mixture of composites to, assemble an aircraft, or before were there more like light alloys to make up the
Yeah.
structure?
Yeah, so previous airplanes are going to be mostly metal, right?
Mm-hmm.
And I think over time, we've made this slow introduction of composite materials as we're figuring out how we do fabrication, processing, the lifetime of composites, things like recycling and repair. So even now, the 787 does have metal aspects to it, right? We have metal frames, we have metal floor grids. It's a mixture of materials.
And you mentioned that we're using epoxy, which undergoes an irreversible chemical reaction. And you mentioned that we also use things like thermoplastics and other parts of the plane. Why do we use this type of reaction in the fuselage compared to like thermoplastic, which has a reversible, and other things that you're talking about, like fiberglass and other composites that we have talked about that have different mechanisms of setting?
Yeah, so the biggest difference between thermosets and thermoplastics, which you mentioned, right, is the ability for thermoplastics to be re-melted down. And that's, to me, that's huge because I think the environmental factor, when you think about these large structures and the ability to recycle these materials over time, thermosets are typically going to give you better strength capability, and not to mention, repair capability. We have a lot more knowledge about how to repair our current material systems. But you will start to see an increase in thermoplastic materials, I think, in all industries because of the ability to recycle, and also the processing for thermoplastics is significantly cheaper. So as you see an introduction of smaller parts, maybe there is a future where we have more structural parts made of thermoplastics.
Cool. And so when I interned at GE Aviation, we learned about CMCs, or ceramic matrix composites. And I know that one of the biggest factors in terms of actually implementing that was like the cost. At this point, it's like higher manufacturing costs. Is that the same for some of these composites that you're working with compared to, other like metals or alloys or things like that?
Yeah, and I think that comes down to the amount of time we've been using them, right? If you look at the history of metal in multiple industries, we've been refining that process for years.
Right.
So I'm anticipating, as we continue to do research, we continue to use these materials, we're going to find ways to more efficiently produce them. So especially from a structural standpoint, right? So an example I think of in that regard is a layup process. So if you're taking pre-preg and forming it into a shape, if you have a really complex shape, most likely that's going to have to be done by hand. But we're trying to go through evolutions of better forming processes to make it even cheaper, and understand how, when we form a composite, what are we doing, right? Where are we putting in places of compression or causing wrinkles or voids that might affect the structure? But how can we design them more efficiently to plan for those wrinkles, plan for those voids, or eliminate them and make it cheaper? So I would anticipate in the future, as we develop more of those materials, that we go through that evolution of making ourselves more efficient.
I guess taking a step back from a little bit of the nitty gritty, could you give us a general overview of the production process of an aircraft fuselage and how the manufacturing of composites may differ from other materials like aluminum alloys? And I guess another question is, what exactly is encompassed in the word fuselage?
Yeah. So I am going to focus on the two sections that I know most intimately. So first, I'll go over the composite process. So the biggest part about a composite fuselage is that typically we're going to call it a one-piece barrel. So what is going to occur in a clean room setting? So that's pretty important, right? So first and foremost, we have a specific environmental setting where we have to lay up this composite material. So that's a big difference that I'll highlight later. But we're laying up the actual structure in the fact that we're taking prepreg, which is the fibers pre-impregnated with the resin, and we're forming it into the shape of stringers, pad ups where we might have frames, corrosion protection using some fiberglass, and then we are laying up the skin around that structure, and then we're curing it in an autoclave to make it one single piece. So after we get that one single piece, you're then going to install what I'm going to call the guts of the airplane. So your frames, your floor grid, your systems, and all of that is going to be pushed into that fuselage after it comes out of the autoclave. So that's typically a little different than thinking about metal processing. You're going to go the other way almost. You're going to form the skeleton and then put the skin over the top of it versus taking the skin and filling up in the guts of the airplane. So very different there, and not the same kind of environmental conditions when you're building a metal airplane. With composites, it's extremely important that we do not introduce any environmental factors that might cause the composite to degrade or introduce foreign object debris or get it past the mechanical life where it degrades the structural property of the material as well. So that is a huge aspect of composite processing and understanding the material. Also, part of composites, I mentioned the corrosive resistance. It's very common for people to see in metal processing, you're going to see green all over the airplane. It's like, why is that green? And it's because there does have to be a chemical coating over the top of those metals for corrosion protection, because over the lifetime of the airplane, we're seeing airplanes that are 30 to 50 years old. We need to protect for corrosion. So you're going to see a lot of that corrosion protection in composites actually built into the composite part. So cured with the one-piece barrel, or application of adhesive or fiberglass in specific areas, or primer applied in specific areas. So very different chemical processing for those two.
And I guess just generally, I know it's not one-to-one because there are always going to be different planes, but which process is faster? Is it the skin in to the inside or inside out approach usually faster than the other?
So I think when it comes to that, it is very dependent on the program, dependent on the need, right? And dependent on the knowledge of the process and how we're set up for a building, right? So when people see something like the 737, we are creating airplanes at a very quick pace, right? We have a moving line. We know that process like the back of our hand. However, the need for a larger aircraft isn't always as high. So the rate, it can be more dependent on what we're going to call the skyline for the company. But I will say, I think from the assembly process, it's probably more similar when you're talking about installing those frames, installing the floors, and installing the systems of the airplane too, right? So all of that's going to be very similar, but the fabrication process is very different.
Gotcha. Okay.
And so you mentioned the autoclave a bunch of times. So I was just wondering, can you dive into that manufacturing a little bit in more detail?
Yeah, of course. So I mentioned we're laying up the actual part in that clean room environment. So that special environment that we're protecting that part before it goes into the autoclave. So the autoclave is the place where we're going to actually cure the material to get it to its final state. So when I talked about that cross-linking of the thermoset, that's where that cross-linking is occurring. So it looks like a really big oven. We're going to be sticking the whole barrel into this massive oven and curing it at a certain temperature and pressure. So what this does is it eliminates voids in the composite. It takes out all that off-gassing that's occurring from those chemical reactions, and it makes a consolidated composite part that cross-linking occurs. You have those strength properties. You are ready to go after that process. But it is this massive oven that we are putting this part into to do that cure process.
Got it. Okay, cool. And so I guess taking a step back to the MSC side of things, so even the supply chain process seems complex in and of itself. And so since there are so many different ways to make an impact as an MSC within this aerospace industry, can you maybe talk through a few options for materials engineers that you've seen throughout your time at Boeing, whether that's supply chain or design or manufacturing?
Yeah, so Boeing has a huge amount of opportunities for people in material science. I think the first thing to comment is that, depending on where your interest lies, you might be more interested in commercial aircraft, defense aircraft, satellites, space aircraft. So there's already a wide range when you just think about aerospace in general, but diving in, I like to kind of think of it in two ways. So I think there are options when we think of technologies within any of those sections of Boeing, as well as functions. So first, from the functions perspective, like you mentioned, like supply chain, design engineering, production engineering, which could be manufacturing engineering, tooling engineering. There's a wide range of functions, liaison engineering. So I believe someone with an MSc background could be put into any of those functions. They do perform different things, right? Someone in design may be dealing with modeling something in CATIA, creating the different GD and E requirements. Someone in production engineering is going to be down on the floor monitoring equipment, monitoring process improvements, implementing something from the statement of work, being very hands-on with the aircraft. And then you have the function that I'm in, which is research and technology. So there's kind of two sections of research and technology too. There's implementing new processes, new materials into a production environment. And then there's this long-term research where you might be researching a material for 5 years for specific structural properties, or you might be researching a new process for the next airplane model. There's a wide range of things there. But then to elaborate on the technologies which factor into these functions as well, you could be doing things in composite materials, metal materials, chemical technologies. So those that corrosion resistance, you could be dealing with finishes from that perspective. You could even go so far to say, I am the thermoplastic expert. Right? So there's a lot of opportunities within all of aerospace for people in materials science. It's just getting into the nitty-gritty of what do you find interesting, and exposing yourself to that. And I think being at a large company like Boeing gives people that opportunity too.
Needless to say that MSCs really can do anything. And I think that's kind of one of the goals with the podcast, is just to show the versatility of materials engineers. So I really loved all of that, because you just touched on so many different ways, even within aerospace, that MSCs can kind of play a role in.
And yeah, I just want to say that I agree a lot with what you said. I think one important thing that I've learned throughout my journey is that like things like design and manufacturing, while might seem more mechanical, having insight of materials and how it will process and how it will perform gives you a completely different insight compared to people with more mechanical backgrounds that just know how to make machines. And so I think that your insight into, yes, we're making machines, but it's going to be working with XYZ, gives so much more insight. And so that while material science isn't needed for the job, material science gives you an edge and a different way of thinking and completely different skill sets to help solve the problem at hand. So I think that you're right. We really can do a lot.
Yes, I totally agree.
Cool. Well, one very intriguing aspect of your role that you're currently in is that you take something that is application ready, and then you're responsible for actually implementing it into production, which is a complex task in and of itself. What does a large scale testing and implementation process look like exactly? And what challenges do you face that people may not immediately think about?
Yeah, so I touched on kind of the two areas of research and technology. And one of those is going to be, for example, developing that material, right? So if I'm developing a material with a supplier over the course of a long period of time, we're then going to hand that off to someone on my team to say, how do I actually build this into the production process? How do I work with all of the folks here, whether that be operations, quality, production engineering, to make sure I have a process that is robust and repeatable and safe for the airplane. So most of the time, my team is going to be taking something that someone has tested at the coupon level, right? So small coupons, material testing, throwing something in an instron to do some like mechanical tension or compression testing and saying, how am I going to use this on the airplane? So they're going to be doing more large scale testing. So this is probably going to look like actual validation tests either on the airplane structure, or it's going to look like large scale tests run at a different site. So I'll give an example of, say, like a mold release for composite, right? We had done a series of tests on small coupons to say, yeah, it does release, and it does release over a period of time. Right? Then my team took it and said, okay, now how does it release over a tool that is 35 feet long and complex geometry? So we would do testing over a series of that larger tool and then expose it to additional things that it might see in the production environment instead of at the coupon level. I think the biggest thing that is challenging is being able to capture the series of risks that come with production and high rate production, right? Because something may be robust in a lab environment or robust to us as engineers, but how is it going to be used by someone who hasn't been researching it for 2 years, right? Who doesn't have the time in the lab to do it, very meticulously and slowly. So thinking about those kinds of risks and capturing them early on and being aware that you might have some learning experiences along the way is a huge part of what makes a successful engineer on my team, and just being able to adapt to those changes and learnings as you make them, right? And knowing that you might not reach 100% success. You're not going to get something that's 100% perfect. So how do we implement something that is maybe an 80% solution, right? Maybe you meet 80% of your requirements. Are you able to get by? Is it still a safe and quality product without meeting those other 20%? So I think those are the biggest things, is just making sure we acknowledge the risks of a production environment.
So how often do you interact with maybe like the user of that material or whatnot, or versus like trying to automate this like new process? Does that make sense?
I would say my team every day, right?
Okay.
So we are extremely integrated into production. I sit on the production floor. We are able to interact with them. We go to their stand-ups. We speak to our operators daily, and that's a very important part of my job. But I would say my team does have a good balance as far as when you mentioned equipment and say like automation. We are interacting with that equipment, and my team is part of making those improvements for automation, like applied learning, applied mathematics, understanding how we actually improve that automation to make a more efficient process for the operator to use. So we are doing all of that every day, from the fabrication process as well as in the assembly and integration side of the house as well.
And yeah, so you said that at first you're on a coupon test, which is very, very small pieces of material. When we're talking about planes, how large do you scale up until you say, yes, this is what it's going to act like on the machine? Like, if we run it at full width for 5 minutes, is it the same as an hour? Or what are the metrics that you guys use to infer, like at larger scales, what it would look like?
Yeah, so I think it is going to be dependent on where you're talking about in the factory. But for an example like that, you do want it to be the most representative of your production tooling, right? So I think what's important, if you had limitations, like say you're trying to represent a 50-foot part and the largest thing you have is 10 to 20 feet, right? It's capturing the risks of what's going to happen if there are some unknowns when I do scale up to that 50 feet. Right. And how do I safely implement something like this, knowing what risks do exist? So what happens if your part sticks? You know, are you going to have a repair process? How long is that going to take? How much money is it going to cost the company if you do have to repair this part? So I think it's weighing those risks of saying, okay, is my test representative enough?
And so if there's like an 80% solution, like you were saying, what types of steps are you taking next to potentially like improve it to the point where it's safe and effective in a full-blown aircraft application?
Yeah. So I think it is extremely important for incremental improvements at that point, right? If you're implementing a solution, I think safety and quality still the number one, right? We're never going to put it in there at the 80% unless it is a safe and quality product and produces a safe and quality product as well. So that 20% is probably going to be those nagging things that, you know, say you have to go to 3 different websites to log something. Say you're fat fingering typing in a certain number every once in a while, and it's affecting the way we track metrics. Or say it's adding some extra time because an operator has to go the extra mile to go get a different product, you know, maybe it's stored in a specific location. So I would think it's smaller things. It also might be incremental ergonomic improvements, right? We've implemented systems for drilling that, you know, maybe we can create a better handle or a better way for our operator to interface with the airplane or the tool itself that we've made. So it's more of those smaller things that I think might go by the wayside when you're implementing something as large as maybe a new material or maybe a new piece of equipment that you might not think about when you're saying, okay, how does this large robot lay up this piece of material? You might not think, oh, like the operator has to walk from point A to point B, and that's kind of silly. Like you won't recognize that until it's already on the floor, already working. And it's those small improvements that really make a difference in people's lives that are building the airplane. And that's really important to me as being a part of production.
And then, so this is more of a general question, but from the problem solving side, what techniques are you using to get to those like details about what exactly went wrong in the process? Because for GE Aviation and for Boston Scientific, I've seen like the 5 whys, problem solving where you're just continuing to ask why until you finally get to the root cause. Is that also consistent with Boeing?
Yes, that is consistent. I do think we have a lot of that 5 why built into our problem solving model. So I think the first thing in any kind of situation is first to know what is the current state of the situation that you're dealing with, the current state of the problem. And I think that factors into that 5 whys, right? So what is happening today and why is it happening? And getting to that, asking those whys it's important because I think as engineers, we are very, we want to solve a problem. We want to help. So a lot of the times, if you're familiar with the process, you can jump to a conclusion of, well, I already know the solution. Here's the solution. And you haven't really diagnosed the problem fully. So we can get into that kind of loop. And I think stepping back and saying, have I looked at all aspects of the problem? Have I involved all the correct stakeholders? And have I asked all the right questions to get to a solution is really important. I think also as engineers, we're very apt to rely on data. And that's great, right? Data should drive decisions, but there is a point in time when data might not point you exactly in one direction, and you're going to have to rely on some interpretation. And that is why we're so successful at our job, right? We have that background experience. We've been doing these kinds of projects or testing, or we're familiar with this material, and we can look at this data and say, okay, it doesn't point me 100% in this direction, but maybe it tells me that I'm leaning towards making this decision, and I can put some rationale behind it. So I think that's a huge part of our problem solving model. But really the 5 whys, that's a good one, because I think getting to the what is the problem, not what is the solution first.
Yeah. And one question I have is that maybe this is more general advice, but when we're talking about airplane and airplane systems and improvements on that, and you said update key stakeholders, that must be a couple of teams at least, like working across the entire airplane. When we get to a scale that big, I know it gets difficult to kind of keep everybody updated and move at a fast pace while still getting everybody's opinion. So from your side, what are some, like, what's advice, or what have you seen happen when you're trying to move fast, but also try to think everything through from everyone's perspective?
Yeah, I think the most important aspect is trying to get people engaged at the beginning. So when you do start a project or you start investigating something, it's giving them some awareness, right? So that's a huge part of that. But we also have built-in processes for that, right? And you did kind of mention that they can be cumbersome. So it's about making some of those processes work for you, right? A lot of people are going to say large company, bureaucracy. That's a huge word that we hear all the time. And that's true, but it's also there for a reason, right? So it does give me a sense of comfort that if I'm going to change something in an aircraft system, that I need to run it through all of these hoops to make sure it's right, right? Like I want to make sure that we've done that. But with the moving fast, I think for a lot of our systems where we go through approvals, we have processes where we're ranking them for priority. So that's pretty big to me, that we get that prioritization correct, and we stick to that process, and we help make the process work for us, right? So if you have to do this documentation, flipping your mindset of, okay, I do have to do this documentation. Maybe you don't want to at that point, right? Maybe you just want, like, it's a simple change. I should be able to do this real quick. It's about leaning in and saying, I need to do this documentation the best way the first time. And that way I can at least make the process work for me, that I'm not delaying it, right? So you're doing everything in your power to say, okay, I'm working with this process and I'm going to try to push it along, versus I'm working against it. So that can be one way to combat some of the bureaucracy.
Gotcha.
And I guess building off of all of this, there seems to be a really good learning opportunity here for MSc specifically. As you said in a previous conversation, that the assembly and integration aspects can often sometimes be like ignored from materials engineering perspectives when it comes to design, and especially with like composites for aerospace applications. So can you just talk us through what is often failed to be considered? And is it like interactions with other subsystems? Is it processing parameters? Is it something else entirely?
Yeah, so this is definitely, I think, a personal experience and like my schooling experience. So it might not be true for everyone, but I found that we were very focused on maybe a more chemical level for materials engineering. And I was able to find more of that application real world experience through getting involved with groups at the university, as well as getting involved with research and getting engaged with industry. So one of the things that I felt like I was missing was some of that mechanical aspect, right? So there was probably some overlap between the mechanical engineering department and the material science department, but some of these assembly processes that my mechanical engineering friends understood well, I had to do some extra effort to learn those. So what I mean by that is drilling and filling processes, some of that automation that's inherent to mechanical engineering, maybe prototyping and machining. Some of that understanding can really help a background in assembly, right? So if running a lathe is not the same as building an airplane, but you might be able to apply some of that understanding of this piece of equipment, this piece of machinery, and how you interact with it to how an operator interacts on the floor, or even just some of the mechanical aspects of something on a production floor or production environment. So I think that's kind of the aspect of saying, okay, now I know these material systems. I know how chemically they interact. I know their mechanical properties. I might be able to do some analysis as far as how do these stack ups behave differently in stiffness or strength. But when I assemble a product, how am I going to do that if it's not just one piece of composite? And I think that's something that people can explore within their material science department, but also can explore on other parts of their university. So it's just knowing that if you are interested in aerospace and you are interested in getting engaged, a large part of that is assembly and integration and systems in an airplane. So making sure that you're exposed to that when you can do some of that exploring, right? And then you touched on the design aspect. I thought what a great part of some of my composites classes was kind of learning how different matrices behave and how to do that analysis. But some of the parts that I wish I could get more engaged in is how does a larger assembly, kind of the same thought process, how does that behave? How do I analyze for that? And how do I design something like that? Where do I even start? Right. So I definitely was missing that aspect in the way I went about getting my degree. And I wish I had focused a little more on the design aspect and, what technologies are out there for me to analyze that, right? We are living in a virtual world. We are living in a world where we have all of this equipment and software at our fingers. So knowing what's out there and knowing how to use it. Like, how do I analyze how a barrel cures in an autoclave? How is resin flowing through the part, right? So I think that's an aspect that I didn't get as much in my schooling in materials science. That might be something that someone could explore if they were interested in those areas.
I think you just did a great job highlighting why we can't get too focused in on one part and that we have to have a good understanding of the holistic system. And one of my favorite examples of this is for Tesla, their Cybertruck. They had a very famous showcase where they threw a rock and then hit their window with a baseball bat. And it was supposed to be bulletproof and not dent. But in fact, when he hit it, it actually shattered. And that was a really good example of they tested it with a rock and they tested it with a bat, but they never tested it with a rock and bat. And so things are going to change as we use them differently. And so having a holistic view, like you're talking about, I think is really important for us as engineers. especially when MSCs are the ones that are trying to apply materials to a system and figure it all out.
Yeah, what steps did you take, like when you realize, like from this mechanical engineering versus material science and engineering? I know you eventually went back to get a mechanical engineering degree, but what recommendations would you have for students who are like still in that space, that learning space, or like in school? And what, like, is it just a Google search? Is it watching YouTube videos or courses? What would you recommend?
Yeah, I really think there's a few things that students can do. I think the first is staying engaged with the MSc department and understanding how diverse their department is, right? There might be some professors who are more focused in specific kinds of materials or specific kinds of research, but knowing that if you do research with one professor, doesn't mean that you can't go spend extra time with other professors within your department, right? And I think that also extends outside of your department too. So if you're interested in machining, if you're interested in mechanical systems, then you should definitely go explore another department and speak to as many people as possible. I think it can be really uncomfortable to approach a professor and say, I just want to talk to you for an hour. I know that makes me sweaty thinking about it, right? So just being prepared to say, what are you interested in? And write down a couple questions. I think other professors are really willing to speak about what they do and share their experience with students. We might just not always take the time to do that as students when we're in school. So that would be the first one. And I think also just to say, like, if you are in one department, you can do research too in another department. It's not off the table. You should definitely look into it, speak to people, the same thought process. Second, getting engaged in those groups in school as well. I think I learned the most about handling composites through being in a team of folks that were building bridges for SAMPE, which is the Society of Advanced Materials and Process Engineering, right? So I learned so much there, and I would have never learned that just through classwork. So knowing that there are groups out there that can offer some of those experiences and looking for them early, right? Because you don't want to get engaged at the end of the year and they've already made their product, their car, their submarine, their bridge. So making sure students do that. And really, I've said the word explore so many times, but being in college offers you that opportunity. So take advantage of it, because there is so much on campus, so much you can learn, and just don't want to miss it.
Yeah. I would say my favorite, I agree that it is awkward to talk to a professor. So one of my favorite icebreakers that I've told my friends to do is that read one of their research papers and then ask if you can discuss the topics from that. And then you can try to organically flow that into, oh, so what other research do you do? Oh, that sounds really interesting. Can I join? And so I think that's also a good tip. But yeah, I definitely say that you learn a lot through clubs and other ways that you would never learn from class, just because the focuses are different and the people are different. So I think it's really a good idea to join clubs.
Definitely.
Cool. You mentioned that non-destructive evaluation of materials has enormous potential for growth in the aerospace industry. What opportunities would this method open up, and how can material science help accelerate this advancement? And maybe first, could you explain what exactly non-destructive evaluation means?
Yeah. So we talked about that evolution of materials in aerospace, right? And the knowledge of how we manufacture with metal, and even the idea of, there are some new materials out there that are really expensive, difficult to process. So how do we get to a point where we understand our current material system as well as we understand metals? a huge part of that is this non-destructive evaluation. So this is technology that we use to understand what the part looks like without actually taking it apart, right? So we're talking about the ability to scan something using like ultrasonic equipment and know, do I have the right thickness? Do I have a void in my composite? You know, is there a piece of tape that was placed in the middle of my composite? And then being able to say, do I need to repair that, or do I need to leave it alone because it's completely fine? So I think there's a huge amount of growth in this space because we need to be able to characterize these complex composite structures to know how we want to improve the design of them, right? So you might destruct a piece to say, do I have wrinkles in here? You know, maybe I have this area where I can't use a piece of ultrasonic equipment to get this weird curvature. So I have to take it apart or cut it up. So I think that's a huge area of opportunity and a different way of understanding a material system than saying, oh yeah, this is what a composite matrix is, right? This is a way of saying, if I have a composite airplane that's 30 years old, how do I analyze that without absolutely destroying it? So that's just a big area of growth. And there's a lot of cool equipment, cool technology. If people are wanting to get engaged into robotics, that's a good avenue to get into, that you really do need to understand materials to have the background and know why you're doing what you're doing and why it's important.
How exactly would robotics play a role in that, or just having a knowledge base? Can you just explain that a little bit more?
Yeah, so I guess imagine you have this big fuselage, right? And you need to be able to scan that entire fuselage. What kind of, am I going to be designing an end effector for a big robot? Like, what does the footprint look like for that? How would a user interface with that end effector? Maybe I need not only a robot on the outside of the barrel, but one on the inside too. How do I build a system like that? And how do I program it to run in a way that I get the data I need? So it's a lot of thinking about that. You have these large structures and you want to be able to have an operator run something from a safe position, right? They want to be safe from the automation perspective, that nothing is going to run anywhere near them, right? As well as ergonomically safe, right? We shouldn't have someone crawling on the inside of a bare fuselage to try and get a piece of data. So I think from that aspect, it's just building more efficient equipment and getting engaged from a robotics perspective that way.
Got it. Cool. And I guess so another aspect of this aerospace industry is just like the seemingly never ending number of subsystems that make up an aircraft. And inherently there's just a lot of moving parts within each system. So you mentioned before that composite modeling could help with understanding the system as a whole. And so I was wondering if you could just talk us through how more accurate, precise composite modeling would lead to further advancement in this field.
Yeah, so I mentioned a little bit about the idea of I can design a laminate, right? I can design maybe a stringer. But what happens when I make that into a structure where I have a stringer and an airplane skin, and now I have elastomer tooling combined with composite tooling all together on this metal cart? You have this massive system that's going through like chemical processing. And how do I know that like such an integral part of composites is curing it to make that final state, right? So how do I know in that moment in time what's occurring in that autoclave? How is that material reacting? And a huge part of that, I mentioned elastomer tooling, right? So they'll often be referred to as bladders in composite manufacturing. So it's going to be some kind of elastomer that is providing pressure along the inside of a part, so you have a consolidated compact laminate. So part of understanding that elastomer is knowing, okay, now I'm thinking about this composite, but also what's happening to that elastomer in that autoclave process, right? How do I decide how long these tools are going to last when I'm putting them through these high temperatures and this very different environment each and every cure cycle? So thinking through that, and how do you model a system? Right. And going back to that holistic view of how we look at parts. So I think just improving on that aspect would give us a lot of insight into a more systematic approach to engineering.
How much would you say the industry knows about it? Like, how complex of an issue is it to try to model an entire airplane full of composites? Is it something that we've done before, or is it like going to be the next evolution of our understanding of composites?
I think it's definitely something we are doing, right?
Okay.
So we have design and stress teams that are doing it on a daily basis. But I think it's about making it more accessible to, say, like a student, right?
Okay.
How do I take something that's available in a classroom setting, or even a program that I can find on the internet, and say, how would I build an airplane out of composites? How would I design it? And I think some of that goes back to, like, I think about senior design projects and people who are interested in aerospace. How do we make that more accessible to people, right? So it isn't people with this background for 20 years in aerospace that are saying, well, we have a material we can load into this structure in CATIA or a modeling system, and I have to do some extra analysis, and it's very specific to us. So I think it's just about making it more accessible to everyone.
Is that CATIA software there's a bunch of modeling softwares like SolidWorks and AutoCAD. So that might be just another piece of advice for students who are interested in this sort of thing, is just to maybe try to get access to some sort of modeling software and just practice and then build up, because starting at maybe something as complex as an aircraft might not be the way to go, but it's
yes.
small steps first.
I definitely agree. And I think that was something that I was thankful I was able to take classes in another department that taught me some of those skills, right? Yeah. So I think that's huge to look into that modeling and get a basic understanding, because even if you don't use it, a lot of engineering functions do. And you might find yourself wanting to design something in your house one day, or design a tool for another job using a piece of modeling software. So I think that's a very useful skill, and definitely comes down to the fact that we're in this virtual environment right now where we're all using our computers a lot. So get exposure to that if you can.
Yeah, especially with 3D printers becoming so popular, everybody could use the skill of modeling. But yeah, today we discussed a variety of topics, from composites to aircraft assembly to future improvements of what we want to see in the space via modeling and simulation. Considering everything we talked about today, if I was a new student coming in who wanted to go into the aerospace field, what advice would you give me?
Yeah, I think I touched on getting engaged in groups outside of your classwork. That is, I just want to hammer home that that's a big one for me, and getting experience outside of a classroom. That hands-on experience is extremely important. But I think from a materials perspective, it's knowing that you can't, if you love aircraft, you love aerospace, you can be a part of that as a materials engineer from many different aspects. So just knowing that and saying, I'm interested in this, and talking to folks and using the time to explore what options you have at your university, it's just really big. And I do want to hammer home too the importance of internships when you can, right? Getting exposure to a work environment is a great experience, and part of being at work anywhere is just knowing how to work with people. So I think being engaged in those groups outside of classwork, really important. But from a materials perspective, I think just if you are interested in composites or metals, even, there is still a lot of work out there. There's still a lot of evolution out there, a lot of development. So if you're interested in the aerospace industry, you can be engaged in it from a research side, even at your university, or the production side, and be a part of the business, be a part of the industry. So there's space to grow, whether you want to go get your PhD in material science and engineering, or you want to go straight from college into work.
Yeah, thank you so much for coming onto the show today. You shared a bunch of very valuable advice and very valuable information as a whole. So we really appreciate it.
Yeah, thanks so much for having me. I really enjoyed it, guys. And I look forward to hearing some more podcasts.
Thank you for tuning in to this episode of the It's a Material World podcast. If you enjoyed the show, consider subscribing and hitting the like button down below. And if you'd like to support us on this journey or simply show off your love for MSC, we actually released merchandise. And if you'd like to check out more of the designs, visit itsamaterialworldpodcast.com/shop or use the link in the description. We'll see you soon. And in the meantime, go change the world.